Okay, so let's talk about Riemann sum and the definite integral. So this is a definite integral. It means the area under the function y equal to f of x equal to x squared. So this is the parabola over the interval 0, 2. So that's why I only put out 0, 2. So the region that I care about is this. Okay. And before we can talk about how we find the region, we have to talk about what it means by a Riemann sum. Okay. So first of all, let us partition the interval that you have, partition 0, 2. And the 0 and 2, it can change. So what I want is to partition the interval that you have in your definite integral. So if I have 1 to 2, then the interval here would be 1 to 2. Okay. So what we can do is we can do even partition. So into n equal subintervals. Okay, so let's say n equal to 4. Okay, the reason why I use n as opposed to a actual number, because eventually I want this n to be to be approaching infinity. So this n will get larger and larger. Okay, so we want to chop this interval into 4 equal pieces. So this is what I get. Half, another half, sorry, a quarter, 1/2, and then 1, 3 halves, and then 2. So the length of each subinterval is 1/2. Okay, and of course, if n is equal to 5, then I will have different cuts. If n is equal to 10, then I have different cuts. Okay, so where you cut your interval, how you cut your interval, it really depends on how you partition, how many pieces you partition the interval into subintervals. Okay, so this is just an example. Then 2, in each subinterval, choose we call it a simple point. Okay, so any point is fine. Just choose a point sitting inside the interval. Okay, so for example, what I can do is I can choose the left endpoint. You can also choose the right endpoint or middle point or whatsoever. It doesn't matter. Like I said, as long as inside each interval, then you are good. Okay. So we have how many subintervals here? 1, 2, 3, 4. So for each interval, we're gonna choose one simple point. So in total, we'll have 4. Okay. So if I want to choose the left endpoint in this interval, my left endpoint is this one. In the interval from 1/2 to 1, the left endpoint is here. For the third interval, so let me actually mark it. So let's call this x1, and let's call this x2. And for the third interval, let's call this x3. For the last interval, the fourth interval, let's again choose the left endpoint, and that's x4. Okay, and once again, it does not have to be the left endpoint. It can be the right endpoint. It can be anything. Like if you want to choose something in the middle, that's fine. Okay, I just want something that's in the interval, and the second point would be something in this interval, and so on. Okay, So then what do we do with these intervals? So then we will have x1, x2 to xn. Okay, so I have n subintervals, then I have n points for each subinterval. Okay, so in this case n equal to 4, so I have x1 to x4, like that. All right, so now I'm gonna compute. I'm gonna compute f of x. It's not necessarily compute, but just quote unquote compute. Okay, so I'm gonna compute f of x1 times the length of the subinterval. So because we're cutting this into equal pieces, so let's just call this delta x. So the length of each subinterval is the same. Okay, so here delta x is dividing 2 minus 0 into 4 pieces. So for each subinterval, it has length a half. Okay, so I want to compute f of x1 times the width delta x plus f of x2 times the width delta x, and I want to continue this till I get to the very last point, which is f of xn and times delta x. Okay, I'll tell you what this give us. So from the graph, f of x1 is 0. So 0 times delta x, that's 0. Okay, because 0 times anything is 0. F of x2 is this number. Okay, so if now I do f of x2 times delta x, what I get is the area of this rectangular region, okay, with the base of the subinterval and the height of f of x2. Okay, and the next one would be f of x3. This is my x3. So f of x3 would be this value, the height of this point. Okay, and if I do f of x3 times delta x, then what I'm getting would be this area. So f of x3, the height times the base. Okay, and similarly, f of x4 will give me this value. So this is f of x4, the height of this point. And if I multiply the height by delta x, then the number here I get is the area of this rectangular region. So now you see that this sum gives me estimated area of the region under the curve. Okay, so this I will call n-term Riemann sum. So in this example, I have 0 squared times 1/2 plus 1/2 squared times 1/2 plus 1 squared times 1/2 plus 3/2 squared times 1/2. So this is a the full term Riemann sum of the integral. Okay? Because we chop the interval 0, 2 into 4 pieces, and for each subinterval we choose a sample point that gives me a height of a rectangular region that later I will use to estimate the area that I care about. Okay? And you can imagine, by the way, there's a reason why I do quote unquote compute, because you won't evaluate, you just need to know the structure of the formula. Okay, so this is it. You don't have to do anything further. Okay, all right, so now you can imagine if I cut this into more pieces, let's say if I cut this into like this is 4, this is another 4 into 8 sub-intervals, and I still, let's say, choose the left endpoint, then the rectangles that I would construct or I would find would be these guys, right? And you can see the number that I get from the Riemann sum would be more accurate than the number I get from my full-term Riemann sum. So this actual area can be obtained by taking the limit of n-term Riemann sums. Okay, so eventually you won't have n approach infinity, and the limit of this Riemann sums will just be the area of the region under the curve over the interval 0, 2. Okay, or whatever you have in here for your lower and upper limits.